Sit back, relax and let's take a smooth dive into the world of testing techniques in software quality assurance. What is a test case? A test case is a documented set of inputs, execution conditions and expected results developed to verify a specific objectives. In simple words, a test case tells us what to test, how to test it, what input to give, what result we expect. Basic structure of a test case. There are two things, field and description, right? The first field is the test case ID. Its description is unique identifier. The second field is the test object. Its description is what we are verifying. The third field is the preconditions. Its description is required state before execution. The fourth field is test steps and its description is actions to perform, right? And fifth field is test data. Its description is inputs used. The sixth field is expected result and its description is what should happen, right? And seventh one, actual result. Its description is what actually happened, right? The last field is status and its description is pass or fail. What are the definitions of test case? First one, a set of test inputs, execution conditions and expected results developed for a particular objective. And second one, a good test case is not just any test. It must be effective, clear, reliable and useful, right? Remember, good test cases find defects, right? First one, have a high probability of finding a new defect. In here, a good test case focuses on risky areas, tests boundaries and tests invalid inputs and covers complex logic. Example, instead of testing enter valid password, login successful, a better defects finding test. Enter 256 character password and check system response. Why? Because defects often occurs at boundaries with unusual data, with unexpected sequences, right? Good test cases are designed to break the system, not just confirm it works, right? Second, unambiguous, tangible result. Result must be clear and inspectable. A test case must provide a result that is measurable, clear, not open to interpretation, right? Bad expected results. System works properly. Good expected result is user is redirected to dashboard page and welcome message is displayed. Clear expected results prevent confusion. Next one, repeatable and predictable. Anyone executing it should get the same result. In here, a good test case gives consistent results, does not depend on random conditions, has controlled preconditions, right? If tester A runs it and gets pass, tester B must also get pass under same conditions, right? If results change randomly, test case is weak. Next one, traceable to requirements. every test case must link to a requirement. This is called requirement traceability. Why important? Ensures full requirement coverage, prevents missing features, helps in audit and compliance. Example, this is the requirement. System shall allow user to reset password via email. They must be connected. This is managed using RTM. RTM stands for Requirement Traceability Matrix, right? Next one, execution and tracking can be automated. In here, good test cases are clear enough for automation tools, have well-defined inputs, and have verifiable outputs, right? Automation tools like Selenium, Cypress, JUnit work best when steps are precise and expected results are verifiable. If test case is vague, automation becomes difficult. Next one, do not mislead. In here, a good test case does not give false paths and does not hide defects, does not assume behavior. Misleading test case checks if page loads. What does loads mean? No errors, all elements visible, correct data, right? It is better to verify dashboard loads within 3 seconds and displays user name and account balance, right? Clarity avoids misleading conclusions, right? Next one, visible. It must be practical to execute. In here, a good test case can be executed with available tools, does not require impossible conditions, and fix within time and budget. What are the examples of not feasible? Simulate 10 million users manually, right? It's better to use performance testing tool to simulate 10,000 concurrent users, right? Next one, black box testing. In black box testing, we don't see the code. We only test based on inputs and outputs, right? We focus on requirements and behaviors, right? Think of it like testing a TV remotes. You press buttons, right? It is the input, right? TV responds. It is the output, right? You don't open the remote to see the circuit, right? Analysis of input and output domain. In here we study what inputs are allowed and what outputs should come, right? This leads to logical partitioning of inputs into interesting subsets, right? This is where equivalence partitioning and boundary value analysis come from. Analysis of observable behavior. We observe how system behaves, how states change, how decisions are made. This leads to follow-like models, state transitions, behavioral testing, right? Even though it's black box, we can create models that look like white box flow graphs, right? But based only on behavior. Risk-based and other techniques. It includes risk analysis, random testing and stress testing. These focus on what is most likely to fail and extreme conditions, unexpected inputs. Equivalence partitioning. If a system accepts values from 1 to 100, do we need to test all 100 numbers? No. It reduces the time required for performing testing of a software due to less number of test cases, right? If 1 is valid, 50 is valid, 99 is valid, and the requirement says accept any integer between 1 to 100, right? What do we assume about all numbers between 1 and 100? Do we assume they behave the same way? That is the core idea of equivalence partitioning. We assume all values inside one partition behave the same way. So, instead of testing 1, 2, 3, 4, 5 and 100, right? Okay, so we test one representative value like 50 because if 50 works correctly, we assume 49, 60 and 80 will also work. Equivalence classes. For input range 1 to 100, how many partitions do we create? Think carefully. We can partition it like this. First, valid values, right? Second, invalid values below range, right? Invalid values below range. And third, invalid values above range, right? Okay, then so how many classes total? You can see 3 classes, right? Valid values, invalid values below range and invalid values above range, right? Next one, boundary values analysis. For input range 1 to 100, in equivalence partitioning we tested 50, 0, 100 and 1, right? In boundary value analysis, do we focus on middle values or edges? We focus on edges, right? Why? Because most defects occur at minimum values, maximum values, just below minimum, just above maximum, right? If range is 1 to 100, what are the boundaries? Lower boundary is 1, right? This is lower boundary, right? Lower boundary. Right. This is lower boundary. And this is upper boundary, right? Wait. Sorry. Right. Now in boundary value analysis, we don't just test 1 and 100, right? We test just below lower boundary, at lower boundary, just above lower boundary, just below upper boundary, at upper boundary, just above upper boundary, right? For range 1 to 100, what is just below lower boundary and just above upper boundary, right? Below lower boundary is equal to 0 and above upper boundary is equal to 101, right? Now let's build the full boundary value set. For range 1 to 100 we are test, 0 just below lower and 1 lower, 2 above lower, 99 is below upper, 100 upper, 101 above upper. Total is equal to 6 test cases, right? We have 6 test cases, right? Now compare. Equivalence partitioning has 3 test cases and boundary values analysis has 6 test cases, right? Why do you think BVA uses more test cases than EP? BVA uses more test cases because defects are more likely to occur at boundary values. So we test values at the boundary, just below it, just above it. That increases the number of test cases compared to EP, right? What are the differences between EP and BVA? EP focuses on groups and BVA focuses on edges. And EP test count fewer, BVA test count more than EP. And EP reduces tests and BVA catches boundary defects, right? Why is BVA important? Many software bugs usually happen at the limits. Boundary value analysis is important because most defects occur at the boundaries of inputs ranges. Decision table. What is a decision table? A decision table is used when there are multiple conditions. We can call it as inputs, right? And different combinations produce different outputs, right? It is also called cause-effect table. Causes are equal to inputs. We can also say conditions, right? Effects are equal to outputs. We can also call actions, right? Example, let's say a login system has 2 inputs. Username correct, password correct. It can be yes or no, right? Now think carefully, right? How many possible combinations are there? Formula is 2n, right? Where n is equal to number of inputs, right? Inputs. Okay. Here n is equal to 2. I said we have username and password, right? We have 2 inputs. Therefore, it should be 2 to the power 2 gives 4, right? Okay. Consider this table. Rule 1. Y, right? It means login successful because both are true, right? You created a complete decision table with 4 rows. You can see it, right? Because number of inputs is equal to 2, right? Possible combinations we can give it using this 2, 2, right? So that's why we have 4 rows, right? Okay, that's the formula. This is the formula, right? Okay. Why decision tables are powerful? First one, focused on business logic. Yes, because real systems often have discounts, loan approvals, insurance rules, and access permissions, right? All depend on combinations of conditions, right? Next one, completeness property, right? Decision tables guarantee every possible combination is considered, right? So we don't miss any case. What are the advantages? It provides complete coverage of test cases and reduce rework. It handles complex business rules easily and simple to understand, ensures no combination is missed, right? Suppose we now have 3 inputs like user logged in, it can be yes or no, right? User has subscription, also it can be yes or no, and payment successful, also it can be yes or no, right? Now how many combinations? Use formula. We have 3 inputs, right? Because logged in, subscription and successful, right? Therefore it is equal to 8, right? According to that rule, we can notice this, right? What do you observe? The number of test cases increases very fast, right? This is called combinatorial explosion, right? That's why decision tables are very useful. They help us organize combinations systematically, right? We use EP when we have input ranges. We use BVA when we test limits. Now, decision table, do we use it when multiple conditions combine to produce different outputs, right? Decision table testing is used multiple conditions combined to produce different outputs. Perfect, right? Decision table testing has the completeness property because it ensures that every possible combination of input conditions is tested, right? That means no combination is missed, no business rule is ignored, no hidden defect remains unchecked, right? Decision table is equal to multiple conditions, business rules, and 2 to the power n combinations and complete coverage. Cause-effect graph. There are 2 related concepts. First one, cause-effect graph, testing technique, right? And Ishikawa or fishbone diagram, right? It is like root cause analysis tool, right? They are related but used slightly differently. In software testing, cause-effect graph helps convert requirements into logical combinations which are then converted into a decision table, right? Cause. A cause is an input condition, something that triggers behavior. Examples: username correct, password correct, user is premium member, right? What about effect? An effect is output, action, state change, right? What are the examples? Login successful, discount applied, access denied, right? What are the examples? Suppose a discount rule, if customer is premium and order amount is greater than to 5,000, then give 20% discount. Now tell me, premium customer is cause or effect? It is cause, right? And 20% discount is an effect, right? What is cause-effect graphing? It is a technique where we identify all causes. We can say inputs, right? We identify all effects. that these things are outputs, right? We connect them using logical operations like AND or NOT, right? Then convert the graph into a decision table. So think of it like this. Like this, right? Okay. Why do we use it? Think about complex business rules. Example, loan approved if income is greater than 50,000 and credit score is greater than 700, right? Or loan approved if government employed but reject if blacklisted, right? This becomes messy quickly. Cause-effect graph helps visualize logical relationships, right? Logical operators used, very important, AND or NOT. Let's test you. If condition says user must enter correct password and OTP must be valid. Cause-effect graph identify causes, identify effects, apply logical operators, convert to decision table, generate test cases, right? Ishikawa or fishbone, right? It is also known as Ishikawa diagram or fishbone diagram. That version is used more for root cause analysis and finding reasons for a problem, right? Example problem, software is slow, right? And possible causes, server load, network latency, poor code, large database, right? It looks like a fish skeleton. Main problem is head, causes, bones, right? Difference. Cause-effect graph is used to model business logic and convert to decision tables, and fishbone diagram is used for root cause analysis. Many students confuse them, right? Next one, error guessing, right? Suppose you are testing a calculator app without using any formal technique. You suddenly think, what happens if I divide by 0? What if I enter letters instead of numbers? What if I leave the input blank? You didn't follow EP or BVA. You used your experience and intuition. This is called error guessing. What is error guessing? Error guessing is a testing technique based on testers' experience, intuition, and knowledge of common mistakes, right? It is usually done after formal techniques during release phase by experienced testers, right? Formal techniques are systematic, right? Error guessing is creative, experience driven, not structured, right? Next technique, random testing. It uses randomness, right? What is random testing? Random testing, also called as monkey testing, right? It's a black box testing technique where inputs are generated randomly. Without predefined test cases, it is often used when there is very little time, no detailed test cases are available. We count to check system stability, right? Why is it called monkey testing? Imagine a monkey randomly, right? Clicking buttons, entering random data, closing windows suddenly, right? If the application crashes easily, it's not stable. That's the idea, right? When is it used? Think about this. If we don't have time to design EP, BVA, decision tables, what might we do? Try random inputs quickly to see if system crashes, right? That's random testing. Let's meet with this part in another session. Bye bye. if you get